Morning, everyone. All right, I just wanted to start the week with a bit of an appeal. Okay. I know it's really hard to stay motivated and to stay focused and to stay on task right now. Okay. Like, I'm feeling it, and I'm usually really good at pushing myself to do anything that I need to, but it's getting hard. And if I'm feeling that way, I can't imagine what all of you are feeling. So first, I just want to say that I get it. Okay, I really do. But I also want to remind you that, okay, the grading policy this semester is pretty relaxed. Like, it's not that difficult. We're asking you to complete at least half of the daily exit tickets from, I'll just talk about my class specifically then, complete at least half of the daily exit tickets I'm posting from April 6th through to the end of the year. Okay, so I'm keeping track of that so I can see exactly how many you're completing. If you've missed some, feel free to go back and turn those in again. I don't care. I just need to see that you turn them in, at least half of them, from April 6th to the end of the year. And then you need to pass your culminating activity. Okay, so for pre-calc, that means getting at least a 1 on our 4-point scale on your final exam that I posted. For AP Calc, passing, so getting at least a 60 on your AP exam video project. It's not hard, all right? If you turn that in and you put any effort into it whatsoever, I can almost guarantee that you're going to get that 1 or that 60%. Those are the only two things you need to complete this semester in order to either maintain your third quarter grade, okay, or to be able to improve it. Okay. So not many of you had an F at the end of third quarter, which means as long as you complete those half daily exit tickets from April 6th on and pass your culminating activity, you're going to get credit for the course. And this is true for every class. I know it's hard. I know it's hard to push yourself to do these things, but I have to say that, especially for those of you in AP Calc, I have been pretty disappointed in the number of you who are engaging, who are turning in your assignments each day or even each week. Okay, there's some of you I haven't seen in weeks, and this is true for pre-calc as well. Just do it, okay? I'm trying to make this as easy for you as possible, and I've said before that I don't think there's anyone who cares more about your learning than I do. Your pre-calc and your calculus learning. And I'm still doing my very best to make sure that you get something, anything out of this quarter, out of this time together. Okay, so for AP Calc, I really want you to pass the AP exam. So I am doing everything I can to make sure that you have a solid review, that you can pass that AP exam, and that you're going to get a grade that you want in this course. Pre-calc, I want you to be ready for a calculus course. So right now we're talking about limits. And as excited as I was to be able to do that in person, I'm still incredibly excited to be able to share that with you via our videos. Please. I'm not asking you to put forth as much effort as I am, but something. I've had a lot of you in class. I've known a lot of you for almost 2 years now. And you're brilliant and you're great people. And you have such bright futures. And I don't want you to risk getting an incomplete in a course now, or not passing an AP exam, or jeopardizing anything in your future because of current circumstances. Like, I hate the way the world is right now just as much as you do, but it is the way it is. And we're all kind of balancing very carefully, like allowing ourselves to experience that, but also doing what we need to do. And I just outlined what you guys need to do. So please, do it for me. Okay, I've had you for 2 years. I love each and every one of you. Just please, let's get through the next 5 weeks together, okay? All right. let's go into today's lesson.
Good morning. Happy Monday, beginning of a new week. We are still exploring the idea of limits. Okay, so you do have an exit ticket due by midnight tonight. It'll be some questions about today's lesson, today's video. Coming back to our notes. Okay, so on Thursday, we talked about what a limit really is, and it's just this output that the function approaches as we approach a specific input. Now we looked at what this means graphically. That's really what this concept of the limit comes from, is just looking at the graph, being able to identify what y values we're approaching as we get closer to a specific x value. But every time we evaluate a limit, it would get really annoying if we had to graph every single time. Okay, so every time we want to evaluate, in other words, solve or figure out what a limit equals, we have a few other methods that will actually help us determine what that limit is. Okay. Now, if a limit is just what this function approaches as we get closer to a specific x value, sometimes we're able to just plug in the x value into the function, into the expression, and it will give us a y value. And that's what the limit equals. Okay. So methods to solve limits, these are incredibly important. Methods to solve limits. The first one is what I just said. We're plugging in an x value, if we can, to determine what the y value should be. Okay, so substitution. So if you want to jot down what this means next to it, that's great. If we can, okay, just plug in the x value to see what the y value will be. All right, and we'll look at some examples in just a second. Okay, I guess we could look at an example here. So yesterday, that last part C of example 1, the limit as x approaches 1 of x plus 1. We could graph this like we did. It's a linear function, and then we can look what happens as we approach x equals 1 from both sides, and we see that the graph is approaching the y value of 2. But instead of graphing that, because that's kind of annoying, are we allowed to just plug in 1 for x here? What happens if we plug in 1 for x? This limit just equals 2, which is exactly what we saw on the graph yesterday anyway. So if we're able to, we plug in the value. Okay. Substitution, very straightforward. Now the issue is that not every function allows us to just plug in a value like that. And in fact, basically the whole reason we're talking about limits, to set up something in calculus with them, is we can't just plug in a value for what we specifically use limits mostly for in calculus. So let's look at an example like part A of example 1. What happens if we try to plug in 1 here? Well, if we plug in 1, we get 1 squared minus 1 over 1 minus 1. It's okay that we have 0 in the numerator, but getting 0 in the denominator causes an issue for us. Okay, it's undefined. So there's no real way of knowing what is this function approaching, because the function itself doesn't exist at that point. So in a case like this, graphing might be helpful. Or is there anything else we can do to this expression to simplify it a little, to get it to a point where we can plug something in? Well, like we did when we graphed it, we factored the numerator, and then we see that x minus 1 cancels out. Now, are we able to plug in 1 for x? Yes, and it gives us the answer we saw yesterday that we get on our graph. The function is approaching the y value of 2. So we call this method This is going to be our second method here for evaluating limits. When substitution doesn't work, we would get a 0 in the denominator, or a negative in a square root, or a 0 or negative inside a log. We use what I like to call our algebra magic. Okay, so all those algebra skills that you've studied over the years, we apply them here. Whether that means factoring and canceling, whether we're dividing two fractions so we multiply it by the reciprocal, maybe we have to rationalize a denominator, or any number of other ways of simplifying an expression, simplifying a function. I just lump all of that together into the single term, algebra magic. So if substitution doesn't work, we try simplifying first. Okay, so that's what we did here. We applied our algebra magic to be able to plug in at the very end. Okay, so methods to solving limits, always try substitution first. If that fails, we try to simplify our expression to get it to a point where we can substitute. Okay. If that still doesn't work, okay, there is a third method, but this method is really only something we're going to talk about in calculus. So I'm going to tell you what it's called. It's a very fun name, one of my favorite names in math. It's named after a mathematician, as most of these things are. It's known as L'Hopital's rule. Sometimes his name is spelled like La Hospital. Okay. L'Hopital's rule. But this is something we're going to talk about in calculus. I'm never going to ask you anything about this, at least applying this in this course. So we're focusing on just 1 and 2. Let's look at some examples. Evaluate the following limits. Now this time they're telling us to use substitution. We have the limit as x approaches 3 of the square root of 2x squared plus 7. Now, like we said before, like we did yesterday or Thursday, we could we could graph this function, the square root of 2x squared minus 7, and then approach x equals 3 from both sides on our graph to see what y value we're approaching. That's tedious, that's annoying. Are we able to just plug 3 in for x? Three squared is 9, times 2 is 18, plus 7 is 25. So this limit equals 5. So we're able to determine that y value, that output that we're approaching, without any graphing at all. We're just plugging in the value. Okay? Because if the function equals something at that x value, of course we're approaching that value. Okay. All right, so substitution, very straightforward. One other thing I want to point out here. It's very important, and I'm going to be very picky about this, those of you moving on to calculus with me. Notice I write this limit notation here, but as soon as I actually plug in that x value, as soon as we actually evaluate the limit, I stopped writing it. But until this point, until we actually plug in that x value, you must write that limit notation in front. So we're going to see that more when we look at the next example, example 3. But just want to bring that to your attention here. Let's finish part B. We have the limit as theta approaches pi of the tangent of theta. So theta, we can use any variable we want in our limit, just like any normal function. Instead of x, we have theta. Can we plug in pi for theta? Tangent of pi. And let's see, tangent of pi, or tangent y over x. We're thinking about the coordinate at pi radians on the unit circle that's -1, 0. Y over x is going to be 0 over -1. which is 0. So we evaluated the limit. The limit as theta approaches pi of tangent of theta is 0. So evaluating using substitution, very straightforward. Let's look at example 3. And they're telling us to evaluate these limits using algebra magic. So that probably means that substitution isn't going to work at first. If the limit as x approaches 1 of x minus 1 over x squared minus 1. Now we can try substitution just to see what happens. If we plug in 1 for x, we do get 0 in the denominator. So substitution didn't work this time. Is there any algebra magic we can perform to simplify this expression first? Well, we can factor the denominator. And notice, since I'm not actually plugging in this x value yet, I did write the limit notation again. Very important. All right, so that denominator is difference of squares. Now x minus 1 cancels. And I still haven't plugged in x equals 1, so I'm writing that limit notation again. In the numerator, we're left with 1. And in the denominator, we have x plus 1. Now let's see what happens, that we've simplified it, if we can plug in 1 for x. We have 1 over 1 plus 1, and it works. Okay. So the second I evaluated, the second I plugged in that x value, I stopped writing the limit because we took the limit once we plug in that x value. So this limit equals 1/2. Okay. And we would see that if we had graphed this, okay, we would have had a hole in the function there, and then we would see that the function is approaching the y value of 1/2 from either side. But we got to skip all that graphing nonsense. Some of you think it's nonsense. I actually think it's quite fun, and go straight to our y value. Let's look at part B. We have the limit as x approaches 0 of this messy function. We can try substitution. If we plug in 0 for x, we get 2 squared minus 4 all over 0. Doesn't matter what the numerator ends up being right now then, because the denominator is 0. So substitution didn't work. We need to try some algebra magic. Now we have a few options here. And it depends on what you can see. In the numerator, okay, we want to try to simplify something. So we could use box method, 2 plus x squared, and then combine our like terms and simplify the numerator, see what happens. So we can do that first here. So there's 2 options here. We'll look at the first one. So 2 plus x squared is 4 plus 4x plus x squared. And then we're subtracting 4 all over x. That's the limit as x approaches 0. 4 minus 4 is 0. And then we can factor out an x from the numerator. We're left with 4 plus x all over x. The x's cancel, and we have the limit as x approaches 0 of 4 plus x. Plugging in 0 for x, we get 4 plus 0, which is 4. Thought it would have a little more room, so I'll go down here. The alternative. This is perfectly fine. We get our answer same way. The alternative is to recognize that the numerator, as strange as it is itself the difference of squares. Okay, we have 2 plus x, which is being squared, and 4 is 2 squared. So we can factor that difference of squares as 2 plus x minus 2 times 2 plus x plus 2 all over x. 2 minus 2 is 0, so we end up with x times 2 plus 2 is 4 plus x all over x. The x's still cancel. We have the limit as x approaches 0 of 4 plus x. At this point, we can plug in 0 for x, and we get the same answer of 4. Okay. Either method is totally fine. They're both different forms of algebra magic. Okay. One is identifying difference of squares, even when it's kind of weird like this. The other is just to multiply that out using box method and simplify from there. Okay. Hopefully, this idea of the limit isn't quite as scary as you thought it might be. Okay. It's just a value the function approaches as we approach a specific x value. We see that on a graph. Instead of graphing, we're talking now about ways of evaluating this algebraically or numerically, so we can plug in the value if possible, okay, just with straight substitution. Or, if that doesn't work, we simplify things a little with some algebra magic to get it to a point where we can substitute it. Complete that exit ticket by midnight tonight. I also encourage you to start looking at the 9.1 independent practice. There's some graphing examples, and there are some examples with substitution and algebra magic as well. Okay, we're going to practice this a lot more tomorrow, and then later this week, we'll look at the rest of our notes. Okay. Please join our Google Meet with any questions. Otherwise, I'll see you in a bit.
All right, that was today's lesson. I hope you got something out of it. Let me know if you have any questions, and I'll see you all tomorrow.